Hello everyone, welcome to another video of the course. In this video, we will solve the problem 25 and 26. Okay, and finally, we will complete the problems of the chapter 1. So, problem 25, repeat example 1.8 if the permanent magnet material is samarium cobalt. The demagnetization curve is given in this figure 1.24. A, determine the point of maximum energy product and the corresponding values of Bm and Hm. Determine the dimensions Lm and Am of the permanent magnet, and finally determine the reduction of the magnet volume required to produce the same flux density in the air gap. So what is the aim of this problem? Here in this example, we assumed a desired value for the flux density in the air gap. We considered this operating point for the magnet, considering maximum energy product, and we calculated the length and the cross-section area of the magnet. So if we are going to have 0.8 Tesla in the air gap and consider the maximum energy product for the operating point, the size of the magnet, the length should be 6 centimeter and the cross section area should be 2 centimeter square. But what if we use another grade, for example samarium cobalt? In this case, the energy product of the magnet is higher, and this magnet samarium cobalt is stronger than alnico 5. Maybe we can reduce the amount of the magnet used, the volume of the magnet. So here are calculations, and just we are going to repeat the analysis. So the part A, determine the point of maximum energy product and corresponding values for Bm and Hm. So let me copy this figure. The BH curve of this permanent magnet, samarium cobalt, is right a straight line, as you can see here. So here we have a triangle, actually. Okay, a triangle here we have. This area, I mean, this one for the samarium cobalt. How we can find the maximum energy product in this case? Because the geometry, the problem is simple. We can find the maximum energy product right on this figure. But when we have a complex pH curve, we should use MATLAB. We need to have the XY points of the HP curve, and we can use numerical methods. But in this case, because we have this triangle, depending on the value of the BR and the value of the HC, these two numbers, this is BR and this is HC, the coercive force, we can find the maximum energy product point. So this is in the middle, this rectangle, okay, that we have, So this is the point that we can get maximum energy product, the maximum area. So if we consider this point, the area is lower than the previous one. And if we consider this point, again, the area will be lower than the previous one. So yes, this is the point corresponding to the maximum energy product. I will show you this also in MATLAB. So in this case, this will be the operating point. Yes, this is the point of HM and BM. Here, this is HM and this is BM. So considering these two new numbers for HM and BM, we can repeat the analysis. According to this figure, I considered these numbers. According to this figure, I considered these are approximate. And based on these approximations, I did this calculation. The remanence flux equal to 0.9 Tesla. Here, I considered a number between 0.8, yes, and 1, close to 0.9, this point. And also, what is the value of HC? I considered it equal to negative 700 kiloampere per meter. Yes, this number. So this is the value of the HC, the absolute value. So here BM is BR divided by 2. Again, I say this is a straight line. And the value of HM is HC divided by 2. If you consider a positive number for HC, this is negative. HC divided by 2. So we can replace these two values in these equations to calculate the length of the magnet and the depth. As you can see, the length of the magnet in this equation is the h in the air gap, length of the air gap divided by the h in the magnet. So we consider B gap divided by mu 0 instead of H gap. And what is the desired value of the B gap? 0.8 Tesla. This is the mu 0. What is the value of HM in this case? Because we considered HC equal to 700, the value of HM will be equal to 350. Okay, so we replace this number 350 times 1E3, that is in actually kiloampere per meter. The unit of the air gap here is centimeter, no problem, because we are going to calculate the length of the magnet also in centimeter. So the length of the magnet will be equal to 0.73 centimeter. What about the cross-section area? We use this equation, neglecting leakage flux. You know that we can have these numbers: 0.8 Tesla for the B gap. The area of the gap is 2.5. I should delete this one, or this is when you want to calculate this quantity in meter square. But here, because I considered this unit centimeter square, the unit of the A gap, right, must be the same as the unit of the magnet, the cross-section area. Here, this is the A gap is 2.5 centimeter square, 2.5. And what is the value of the BM? Is the remanent flux BR divided by 2. we consider it Br equal to 0.9 divided by 2 is 0.45. Yes, 0.45. So if you replace this number here, the cross-sectional area of the magnet will be equal to 4.44. So finally, we can calculate the volume of the samarium cobalt permanent magnet. Here, in this case, the volume of the samarium cobalt will be equal to LMAM, these two numbers, multiplication of 0.73 times 4.44, that is equal to 3.23 centimeter cube. What was the volume of the all-nickel magnet? Was equal to 6.06 times 2.1, that is equal to 12.75. The ratio is 0.25. The volume of the samarium cobalt magnet is just 25% of the all nickel. Yes, using the samarium cobalt magnet, we can generate the same air gap field using a smaller volume for the magnet. This is important when you design a permanent magnet motor and you have to consider a low volume for the motor, right? To design a high power density motor, compact design. Yes. So we will discuss this in detail more in the next chapters in future when we discuss special motor types. But this is the point of this problem. As long as we use a, a stronger magnet, we can reduce the volume of the magnet needed to build up a desired value of the flux density in air gap. So let's consider the energy product here. What is the value of the energy product? 0.95 times 42. So here, 0.95 times 42 is 39.9. This is the energy product, is B times H. Maximum of this product for the alnico is 39.9, okay, kilojoule per meter cube. So now let's calculate the maximum energy product for the samarium cobalt magnet. We should write here 0.45 times 350. As you can see, the energy product is right 157 for the samarium cobalt. So what is the ratio of these two numbers? 39.9 divided by this one. As you can see, the ratio is the same, the ratio of energy products and volumes. So yes, the important point of this problem. And we calculated the amount of the reduction in the volume. So let's repeat the analysis in the ANSYS Maxwell software. Considering a new material, I have found this material. You can pick it up from the library of the ANSYS Maxwell. Samarium cobalt 24. Okay, so these numbers are close to what we have in the problem in this figure. So in this case, let's use the exact numbers provided here we can set the magnet material and compare our solution. So from here, let's set the material of the magnet to samarium cobalt, and here is the SMCO, the direction of the magnetization. You can see here, this is the value of the HC, coercive force. So let me copy, and this is the relative permeability, right? The slope of this line. So in MATLAB here, let's set these parameters for the problem 25. Let me copy this figure again. Okay, so suppose we have something like this, and this is the HC, this is BR. So if we have the slope of this line, the slope of this line, so what will be the equation of this line? Yes, will be equal to B as a function of H is equal to the slope times H plus HC. Yes, when the value of the H is equal to negative of HC, I considered HC a positive number, absolute value. So when the value of the H is equal to negative HC, the value of the B is 0. Yes, correct. When the H is equal to negative HC, coercive force, the B is equal to 0, this point. And when the value of the H is 0, the value of the B is BR, remanence flux. So when we set H equal to 0, the value of BR will be equal to the slope times the value of the HC. So here we have these numbers. This is the relative permeability. Let me copy this for SMCO24. Here is the slope. Paste this number times mu 0. The coercive force. Let's copy this and paste this here. HC. The value of the HC is in ampere per meter. This is the slope, and this is the BR, remanence flux. Yes, this term. So I consider 1000 points from negative HC to 0 to just plot this line. And here is the value of the B, this equation. Yes. So we can plot the HP curve of the magnet. I consider the left axis first to plot the BH curve. Then I calculate the energy product, B times H, the pointwise multiplication, right? B is a vector, H is a vector. Here we define these two vectors. We calculate the energy product, and finally we can plot it. Then how we can find the BM and HM corresponding to the maximum energy product? So using these three lines of the code. Here, let me place a breakpoint, just run the code up to here. Yes, you can see the BT, the BH curve of the magnet. We have plotted it, and this is the energy product. Yes. So here you can see these numbers. Let me reduce the size here. I want to explain this point. So here we have these important numbers. Okay. Here you can see the value of the BR considering this axis, and this is the value of HC. Here we have maximum energy product. The maximum energy product occurs here. Yes. So you can check the numbers. So this is the value of BM and the value of HM that we have here for this point here. So how we can find this point? You know, we have this vector energy product, and we need to find the location that we have the maximum value. So if we consider this vector x equal to 1 5 6 8 3 5 1, what is the maximum value of the x? Is equal to 8. So 8 is the element number 4 of this array, this vector. So x4 is 8. So when we use the max function, we can get both max value and the location that we have the maximum value. The location is 4. So here just I get the maximum energy product and the location. This is the HM and this is the BM. We considered 1000 points. That is enough. So then we can plot the operating point and use fill function to plot a rectangle. This rectangle, to plot this rectangle and highlight the maximum energy product area. To plot a rectangle using fill function, you need to specify the corner points of the rectangle. These points. I specified the xy coordinates of these points to plot a rectangle. Finally, we can calculate LM and AM. So if I run the code, here you can see the BH curve maximum energy product area. This is the energy product curve. Okay, and the operating point that we have. As you can see, HM is negative 378. The value of the BM is 0.5 Tesla. This is the area, the maximum product of the B and H. So, what is the value of the length of the magnet? Here you can see the numbers. The length of the magnet is 0.67 centimeter. The area 3.96. So let's adjust these two numbers and repeat the simulation. Here, the length of the magnet 0.673. The width of the magnet is 3.9644. This number. And Yes, we can repeat the simulation. This is vacuum 1 again, neglecting leakage flux. I can run this analysis setup to check the operating point that we have here with the numbers that we calculated in MATLAB. These calculations are considering these approximate numbers, okay, for the samarium cobalt. But because in the ANSYS Maxwell we used this material in the MATLAB, we considered the material that we have in the ANSYS Maxwell anyway. So here, this is the average value of the flux density in the magnet is 0.49.5. Yes, the same number that we have here for BM. What about the air gap? We have this amount of the flux density in air gap, okay, and this is equal to negative 384. What was the value of HM? This one, that is close. So it means that our calculations are correct. So again, you can consider the material of this region equal to the vacuum and consider leakage flux and compare, right, calculations. Anyway, so what is the next problem? Problem 26. In this problem, the aim is to repeat the same calculations but considering this permanent magnet material, neodymium, iron, boron, NdFeB, right, material. So yes, as you can see, for this material, we have this HP curve. Yes, we have this HP curve. And as you can see here, the maximum energy product for this permanent magnet is higher than this one. So we can reduce the volume of the magnet more. So here in this figure, approximately we have these two numbers. Remanence flux is 1.3, number here 1.3 Tesla. The value of the HC approximately is 980 kiloampere per meter. So you can repeat the same calculations, replace numbers. Again, let me delete this. This is in centimeter. Okay. So we will have these two numbers for NdFeB material, permanent magnet. The length of the magnet is 0.52. The area of the magnet is 3.06. Finally, we will have this ratio. The volume of the NdFeB magnet is much lower than the value of the all nickel magnet. Yes, because we have a high energy product for this magnet. Interesting. So here in the ANSYS Maxwell, I found this material close to what we have in this figure 24. This is the material. You can pick it up from the library. Here we have this pH curve for this material. You can see the data, these 3 points. This is the value of the HC when the value of the B is 0. So let me copy the code of the problem 25 and paste it here for this problem 26, just changing these numbers. This is the value of the HC. So let's copy it here. And this is the, what is the value of the slope? This is the BR. Okay, this is the BR. In this case, we have the value of the BR. In the previous case, only the value of the HC and the relative permeability are specified. In this case, we have the value of BR also. So let me copy this. This is the value of the BR. We can calculate the slope that is equal to BR divided by HC, depending on the numbers that we have in ANSYS Maxwell. We can do these calculations. In this case, we have both BR and HC. In the previous case, we had HC and the relative permeability. Anyway, so if I repeat the analysis, you can see in this case, we have this operating point. The value of the BM is 0.65, and this is the value of the HM close to 500 kiloampere per meter. Yes. So what are numbers that we have in this case? The length of the magnet is 0.51. So let me change the material of the magnet first. Also, you can see the direction of the magnetization, correct. The length of the magnet, 0.511. This number. The width of the magnet, 3.04. So, here we have 3.04. So, let's repeat the analysis. Analyze to calculate the operating point using the ANSYS Maxwell and compare with what we have in MATLAB. Check our calculations. Yes, the average value of the flux density is 0.65. The value of the flux density in air gap. And here is the value of the intensity, negative 506, close to this number. HM, perfect, right? So, as you can see, we can calculate these numbers using these formulations and then compare with what we have in the ANSYS Maxwell software. So finally, let me consider vacuum for the region and repeat the analysis for ND FEB magnet and include the leakage flux in the finite element calculations just to compare numbers. Here, as you can see, this is the value of the B in the magnet, 0.87, the value of the B in the air gap, and this is the HM. So here we can select all, plot, flux, lines. Yes, you can see the flux lines and the leakage flux that we have here. Yes, we have this amount of leakage flux. Because of this, we have reduction in the value of the air gap magnetic field. So anyway, you can repeat the same analysis, and maybe you can also consider other grades available in the library of the ANSYS Maxwell and compare your calculations. Anyway, this was the last problem of the chapter 1. we have completed all problems of this chapter. I hope you found these videos useful for your exam for the chapter 1, and let's continue solving problems of the chapter 2 in the next video. Thanks for watching.